Hello everyone, let us continue with solids of revolution, the volumes of solids of revolution. But now we just want to look at another interesting method of finding the volume of a solid. For instance, what if we want to find the volume of a solid generated by a revolving the region bounded by the graph of say, let us be specific. Say you have a graph y equal to 2x squared minus x cubed, given like this. Don't worry about how to draw this, it's given free of charge. But now you are rotating this about the y-axis. Then you want to find the volume of the solid generated. How are you going to do it? Now, you will recall that the methods we have just discussed will say, okay, draw your representative rectangle perpendicular to the axis of rotation. So we may draw our rectangle like this, right? So if we draw it like that, what does it tell us? It tells us that we must integrate with respect to y. This is our y-axis. We integrate with respect to y because we'll have dy. Now, if we are to integrate with respect to y, we must rewrite this in such a way that we can write x equal to something in terms of y. Is that possible? I don't think so. So we come up with another method called, we say this is volumes by cylindrical shells. We have discussed this in detail in our notes. You can check how we came to derive the formula, but I just want to give a rough summary of what is happening. So instead of drawing our representative rectangle perpendicular to the axis of rotation, because we can see that will be it will be difficult to make x subject to the formula here, we draw our representative rectangle parallel to the axis of rotation. So if we draw it parallel to the axis of rotation, it is telling us that we are going to integrate with respect to x. All right, parallel. Perpendicular, it's with respect to y. We want to integrate with respect to x because we want to have to worry about making x subject to the formula here. Secondly, we note the following. If we do that, let us just take note of this. We are rotating this about the y-axis. So if we do that, we may have, there will be a time when our rectangular strip will be on this other side, right? So if our rectangular strip is on the other side, what kind of an object do we have? Now, if we concentrate only on our rectangular strip, we will observe that when it is on this side, then we will have formed something like this. We'll have formed something like this, an object which looks much like this. So it's kind of a cylinder, and this graph, we may look at it going all the way like that, but let us just concentrate on the rectangular strip. So if we do that, this will be a solid, this will be a solid, because that's where our rectangular strip is moving, and then like that. But this is a solid with a hole in at the center, isn't it? What we are interested in now is what is the height of our solid. What is the height of our solid? And what is the radius when we move from this point, which is the center, to our rectangular strip? How far is our rectangular strip from the center? So for our height, we can see that the height of this rectangular strip will be given by y, the values of y, because it will range. This thing is not fixed, it can move around this graph like that. And then when we look at the radius, this is the x-axis, we can see that it will just be the value of x, which is moving like that. So we are saying that the volume of our solid V will be given by 2 pi, because we are adding everything, the integral from A to B, and we talk of the radius, which will represent by x. Then we talk of the height, which will represent by f of x. Then we talk of the thickness, which will represent by dx, like that. So you can check on page 42 of our notes, and then you will see that we have explained this formula. So this is the radius, this is the height, and this is the thickness, like that. So if that is out of the way, then let us go back to our problem, because we said we want to find the volume of a solid generated by revolving the graph given by this around about the y-axis. And now we're going to do that. So we have said that V equal to 2 pi, and then in this case, maybe I should draw it for you again. So what we have is this, our graph is like this, it will cut at 2 here. This is y equal to 2x squared minus x cubed. Then we draw our representative rectangle parallel to the axis of rotation, because we are rotating here. And then we have observed that the radius is just x, the height, this is just given by that graph. So V in this case is 2 pi, the integral from 0 to 2 of our radius, which is x, multiplied by our height, which is 2x squared minus x cubed, and then dx. If you manage to do this, then it will be easier. The rest becomes easy. Okay, so we continue. This will be equal to 2 pi, the integral from 0 to 2 of 2x cubed minus x to the power of 4 dx, like that, which gives us 2 pi. That one, if we integrate, it will be x to the power of 4 divided by 4, which will give us a 2 here, because we already have a 2 there. And then minus x to the power of 5 over 5. We're integrating from 0 to 2. And when we substitute, we have our 2 pi. 2 to the power of 4 is like 2 to the power of 3, 8, minus 32 over 5, which is 40 minus 32 is 8 times 2. It's 16 over 5 cubic units with a pi there. So the next example says we should find the volume of a solid generated by revolving the region bounded by the graph. Take another one similar to what we've been doing. 4x minus x squared, y equal to 0. Then about the line x equal to 6. About the line x equal to 6. So if you draw the graph, we have just a parabola like that. This will be a 4. Then our line 6 is here. We are rotating it there. Okay, so again we can see that we cannot integrate with respect to y, because that will require us to draw our representative rectangle perpendicular to the axis of rotation, and that will require us to make x subject to the formula, which is not easy. So this is y equal to 4x minus x squared. Fine. Now we draw our representative rectangle parallel to the axis of rotation. This is our radius. This is our radius. Okay, so how do we formulate the integral? So we can see that v will be equal to 2 pi, the integral from 0 to 4. Now we know we need our radius, we need our height, we need our thickness, like that. This is going to give us 2 pi, the integral from 0 to 4. What is our radius? The radius is the distance from this line to any value of x here. Remember, x is just moving along this x-axis. So this distance is 6 minus any value of x. It can be here, it can be there, anywhere around here. 6 minus x. And then we multiply by f of x, which is 4x minus x squared, then dx, like that. This is going to give us, as you can see, when we remove the brackets and simplify, okay, we can do 2 pi 0 to 4. This will be 24x minus 6x squared minus 4x squared plus x to the power of 3 dx, which is 2 pi here, the integral from 0 to 4, 24x is lonely, and then minus 10x squared plus x cubed dx. And then we can go on to have 2 pi, then we integrate. Then the first one will be 12x squared The second one will be 10x cubed over 3. The third one will be x to the power of 4 over 4, like that. We're integrating from 0 to 4. And then when we substitute, we'll get 2 pi. You put 4 there and so on. You get 128 over 3, which will give us 256 over 3 with a pi. And this is approximately 268.08 cubic units. So one can say the following. You will observe that this method can also be used sometimes to solve other problems which can be done using the washer method. But it depends which one is easier, because sometimes you may try to use this and it is a bit more complicated, it's a bit more involving than using just straight away the washer method. Then the washer method is a generalization of the disk method. How? Let me give you a summary. Because for disk, we are talking of v equal to the integral from a to b of pi, say y squared, f of x squared dx, right? And then for washer method, we say v equal to the integral from a to b of pi into outer radius f of x squared minus inner radius g of x squared. You see, you can write your pi here, you can write from a to b, you can write your dx here, you can write your dx here. And if you have something like this, when you simplify, you can see this is common. So you can take your pi, your a to b out, then you have your f of x squared minus your g of x squared dx. So if you compare this method with that one, they're the same. The difference is in this one, g of x is 0. If you take g of x equal to 0, then you are back there. These two methods, you draw a rectangular strip perpendicular to axis of rotation. It's important. And then we have cylindrical shells, or simply the shell method, where now you draw your representative rectangular strip parallel to the axis of rotation. The formula is v equal to 2 pi, the integral from a to b of the radius, which we usually use x. Most of the problems we just use x. We want to deal with y for this method. And then our f of x as it is, then our dx. Then you must be careful when we come to talking about the radius, because it's not, sometimes it won't be that obvious. For instance, in this example, the radius was not that obvious. And then here we draw representative rectangular strip parallel to axis of rotation. And then if you manage to do that, then you integrate. These are the three methods that we are interested in this year.